were talking about whether we could apply his, evolution prediction models to predict antibiotic resistance against some like novel compound. Our conclusion, Brian, was like the training data doesn't exist because there are like insufficient sequence data for antibiotic resistance in the context of like some specific scaffold, right, or something like that.
I think the kind of the advantage of viruses is that there's a lot of surveillance data available with which to train the models, and it seems to be less common for antibiotic resistance. And the results that we had for tuberculosis were only possible because of private data set owned by a large government that was able to train that we used to train those models. But in terms of public data sets, there's some resources, but I don't think the sequence complexity is enough.
Canonical time horizon is 10 years, right? I'm hoping that we can do this a lot faster than that. So a lot of the molecules that I found and continue to find. So right now we have a nonprofit that's set up to attempt to accelerate the rate at which these compounds can get into through the IND process into phase 1. If I'm going to be like a hyper optimist, we can maybe shave a few years off of that 10-year horizon. But still there's fundamental efficacy and safety hurdles that we have to clear in humans, right? And being able to predict what these molecules are going to do in humans before running the experiment, it's we're just not there yet.
The work you're doing, I think, can get products to this point much more quickly. You still have the other points, and then if there are innovations of AI or other things, there are other steps that will continue to be bottlenecks that are demanding new solutions.
I think it's a question of uniform data availability. That's what I'll call it. A ton of this clinical trial data and stuff like this. This all exists, right? But a lot of it's housed within pharma companies who don't make it public, right? So it'd be nice if there was a global sort of consortium that could curate all of this existing human human clinical toxicity data sets and disseminate it to people who are doing drug discovery programs, right? And then we could be in a better position to potentially train models that could predict with some reasonable accuracy whether some new molecule is likely to display some form of human toxicity when it goes into a patient. You know what I mean?
And there's certainly a global effort in bioinformatics to get genome sequences available. The question is, will there be similar efforts by pharmaceutical companies to share what is a global good, but it's also proprietary information? We have to keep in mind that many pharmaceutical companies have left, the large ones have left antimicrobial development because it's high risk with, it's often low benefit with high risk.
It's very accessible to just anyone to kind of learn the underlying tools and techniques in machine learning in a way that, say, doing a big drug screen is not. So, but then in terms of data generation, I think a lot of the it's really important that these data sets are not biased towards certain geographies in the world, and so I think global surveillance and not biasing the data towards more resourced institutions, especially in training these models, is definitely extremely valuable.
So for what I do, the trickiest part is gathering the training data with which to train the models, right? So once this data exists, it's not private. I'm not hiding it. We publish it, when we write papers. So this data exists in the public literature. And I think it's to everyone's benefit. The more people who are playing with these data sets and looking at all of the things that we miss, it's all going to contribute to, the eventual discovery and development of new antibiotics. And I feel like the barriers to entry now are sufficiently low that, there should be a global community of, interested and invested people leveraging these approaches to solve, in our case, antibiotic resistance, right?
These are transformative, I think, in disruptive technologies You've heard some examples that there will be many dead ends or misdirections, but there will also be unanticipated directions, applications, successes. These will come in part from experience, but in part from clever people applying these things in ways that other people had never thought about. Even dead ends will highlight the need for new directions or problems with existing data. Number two, there are some directions that should be of greater value for the management of resistance. Drug design, you've heard about phenotypic and genotypic outbreak detection, response and modeling, clinical decision support at a high level. Also, there's this idea of clinical decision support for individualized medicine. Point number three, bioinformatics, genomics, moving more from phenotypic monitoring to genotypic. Not only the sequences, but the three-dimensional structures of these potential drugs, the three-dimensional structures of the target sites. Number four, to recognize the limitation of the black box approach. The thing is, people just trust machines, but they're not aware of their biases, the limitations. It might be very good for certain things, like for me, for the large hospitals. It doesn't work for a lot of our small hospitals with the large data volume. You have these enormous confidence intervals. And then you always have unexpected things. Finally, basically, what are the key applications of artificial intelligence that facilitate, that help facilitate and national policymakers that they should be exploring now, touching on Satya's point? How do we communicate findings to policymakers? How do we highlight the limitations and strengths? What are some of the biggest areas where some of these things could be applied in the next 5 years?